Okay, looks like we're up and running. Simple question here. What do you get when you add these three graphs together? A linear graph, cubic, a constant. What's it mean to add those three graphs together? Pause the video, think about it, and see what you get for a graph. And I'll just keep talking. Well, let's actually give some names. Let's give the cubic our first graph, x minus 2 cubed. Our second graph, we'll call that one minus 4 times x minus 2. We have a point of intersection at 2, 0. And our third graph we'll call y3. We'll call that constant of 3. Well, I think if you add them up, you get x minus 2 cubed minus 4 times x minus 2 plus 3. Okay. But you also get y1 plus y2 plus y3 on the left side of those equal signs. And that's what you want to be considering when I said add them up. You're adding up the three y values. And you're also adding up the rates associated with those y values at each instant. And so what immediately comes to mind here is these two graphs have no altitudes. They're roots. They intersect at 2, 0, but this one up here is 3. So if I add up 0, 0, and 3, then I'm right there. My graph, this graph is going to pass through the coordinate, and you can see it, 2, 3. It also is going to take on the rates of change at that instant. And the cubic is not changing at 2. It's flat. And so is the constant. Constants don't change. That's why they're called constants. So it assumes the linear aspects, numerical change, and it's going to mimic that for a while. Question is, when does it stop mimicking? Well, pause the video and think about it. I'll just keep talking. It actually, on the left side, at some point, the cubic is going up at the same rate that the linear function is coming down. And when that happens, numbers aren't changing. You're going to get a max somewhere up here. Okay? Maybe even a little closer to that, right? Because the cubic is contributing an increase. Linear is always decreasing. And I would say right about here, somewhere in here, we get going up the same rate you're coming down. And we also know that if you put a 0 in, because if you multiply this out, and I did, I wrote it somewhere, it becomes x cubed minus 6x squared. Obviously, I have a candle in here to make some points, plus 8x plus 3. And the first thing we notice is 8x plus 3 is the slope of the tangent is 8, and the y-intercept is 3. That would happen, I don't know, somewhere up here, but that's 3 units. And, oh, so it's going to be right there, right? And so we're beginning to get a little bit of a look here. And now the question is, what is that x value? Well, it turns out, and what is this most important place, obviously, is what's happening there. And that's happening right here. And that obviously is from minus b over 3a, completing the cube process. 6 divided by 3 is 2. So we got a point of inflection at 2, 3. And that's what the graphing form is. And this is 4 terms. Harder to add 4 y values than 3. So that's what a graphing form is. It cuts down on the number of singular terms and their effect on the conglomerate. So there are some simple formulas that find these x and these y's. this x comes from h minus the square root of minus m over 3a. And you can check that one out. This is often referred to as HK. Well, I don't know if it's often referred to because I don't see cubics in graphical form very often. But we can call it HK. It's where the pattern emanates from. And H in this case is 2, M, the opposite minus 4 is 4. And 3 times 1 is 3. All right, so that's pretty darn close to 2 minus the square root of 1. All right, so but a little bit more. So we're a little bit, we're around, oh, I don't know, 6/3 is square root of 2, which is 1.41. So I don't think we have to get exact here. I think I did throw it in the calculator just to get a decimal sense, and I believe it was I had it somewhere, 0.845. Okay, but this is exact. And I wasn't sure what that was. I put it in the calculator. It came out as 6.079. So I wouldn't have known those decimals, all right, without, I think, the help of a calculator. But that's a little bit more than 3 units. So we're a little bit more than 3 units in the other direction before it turns. Right, and so now that is our graph. It's got 3 roots, bumpity, bumpity, bumpity. Right, and this would then be 2 plus the square root of 4/3, that x value, and we'd be going down, I guess, negative 0.079 would be the minimum, local min. And I'm just doing video because I think it's important for you to consider when you're, got a bunch of terms, graphing forms give you fewer terms. So we can do a quadratic very quickly. Let's say y equals x squared plus, let's make it 2x squared plus 12x minus 5. All right, so what do you have? You've got pretty narrow parabola. You've got something going through the origin at 12 to 1. Then you got minus 5. Those are the 3 graphs that you would have to try to add together and their rates. Or you can put it in graphing form, which is 2x what? 2 goes into 12, 6 cut in half is 3, 3 squared, 9, 18, so minus 18 minus 5, I believe, minus 23. Let's put a negative 3 in. Negative 3 minus 36 cut in half minus 18 minus 5. Yeah, okay, so that's correct. And so what do we have here? Well, at negative 3, we've got a vertex and going up 2 to 1. And we got the graph of minus 5. Those are the 2 terms. What's easier to envision what the graph of adding those 2 terms together is than when you got 3. And the same thing with the cubic. I think when you get to the quartic, I don't think the graphing forms help much. Too many terms to really consider, but still can do it. So is that all I wanted to say? Yeah, I really wanted to highlight this, right? Because we're starting rational functions. And so what do we have for rational functions? We have y equals, let's say 4x plus 3, 4x plus 8 over x minus 2. All right, well, that's really 2 graphs, 4x plus 8 and x minus 2, something like that. And then we'd be talking about dividing one y value by another. And that's really helpful, especially when you get over here near 2, because that y value right there is such a small negative point. Oh, we can make that altitude right there very small. Whereas when I put 2 into the numerator, it's near 12. Then we can see that this graph is going to be undefined, and at that instant, heading to negative infinity. And that's the kind of thinking we want to try to be able to do in the second half of the semester. Deepen our understanding of graphing and the functions you're looking at. All right, so that was just a quick little something to think about. So as you start graphing more difficult situations, keep in mind, look at those Y values. You can add them, you can subtract them, multiply them, divide them, do all kinds of things, and that'll help you understand composites too. All right, that's just a quick little video on something I wanted to highlight.